I'm going to give you a game a 10-year-old can understand in under 20 seconds. But there's a catch. The best mathematicians on the planet have spent almost 90 years trying to prove why it always works. And so far, nobody anywhere has managed to do it. You already have their attention. So here's the game. Stick around because by the end, you'll understand exactly why this simple game has stumped every mathematician who has ever tried it. Pick any number you like, any number at all. If it's even, divide it by 2. If it's odd, multiply it by 3 and add 1. Then repeat the exact same rule over and over on whatever number you get. That's it, that's the entire game. 2 simple rules. Let's actually try it together right now. Let's start with 6. 6 is even, so we divide by 2, 3. 3 is odd, so we multiply by 3 and add 1, 10. 10 is even, so 5. 5 is odd, so 16. 16 is even, 8. 8 is even, 4. 4 is even, 2. And 2 is even, 1. 6 steps, and we landed on 1. Notice how the numbers bounce around before settling down. Up, down, up, down. Mathematicians actually have a nickname for this pattern: hailstone numbers. Like a piece of hail bouncing up and down inside a storm cloud before finally falling to the ground. Now let's try a number that looks almost identical, 27. Watch what happens. 27 climbs to 82, then 41, then 124. It keeps climbing past 300, past 1,000. It eventually rockets all the way up to 9,232 from a starting number of just 27. And then it comes back down. It takes 111 steps in total. But eventually, no matter how wild the ride, it still lands on exactly 1. Here's why this feels almost believable. When a number is odd, the rule forces it to become even immediately afterward. Multiply by 3 and add 1, and you always land on an even number next, guaranteed. And once a number is even, it immediately gets cut in half. So on average, across many steps, numbers tend to shrink far more often than they grow. That's the intuition mathematicians have for why it probably always ends at 1. But probably and on average are not the same thing as a proof. A single, rare number that kept dodging that shrinking pattern would break everything. Change the rule just slightly. Say multiply by 5 instead of 3, and everything falls apart. Some starting numbers under that version spiral upward forever and never come back down. The exact number 3 in this exact rule seems to sit right on some kind of knife edge. Nobody fully understands why that specific number makes all the difference. No matter where we started, we ended up at 1. Try it yourself right now with any other number you like. 9, 100, your birth year, it doesn't matter which one you pick. You'll always land on 1, eventually. Or at least, that's what it looks like. Mathematicians didn't just take this on faith. They handed the problem over to computers, and computers checked it extensively. Not thousands of numbers, not millions. Every single number up to nearly 300 million trillion has been tested. That's roughly 2 to the power of 68. Distributed computing projects, running on thousands of volunteers' computers worldwide, have spent years grinding through this search. Every single number tested eventually reaches 1. 0 exceptions, not a single one ever found. So, case closed, right? Actually, no. In mathematics, checking examples is not the same thing as proving something. Even trillions and trillions of examples. A real mathematical proof has to work for every number that could ever exist, including numbers so large no computer could ever actually test them. There could be one single number out there, one counterexample, that breaks the entire pattern. A number that spirals upward forever and never comes back down to 1. We simply haven't found it. That doesn't mean it isn't out there somewhere. And that's exactly why mathematicians can't just declare the case closed. This same careful skepticism is exactly what mathematicians apply to other famous unsolved problems too. no matter how much data seems to confirm them. This problem actually has a name. It's called the Collatz Conjecture, and that word conjecture matters. In mathematics, a theorem is something rigorously proven beyond any doubt. A conjecture is something that looks true, that probably is true but hasn't been proven. That's exactly where this problem still sits. First proposed in 1937 by a German mathematician named Lothar Collatz. That's almost 90 years ago. Since then, no mathematician anywhere in the world has been able to prove it, and no one has found a counterexample either. It sits in this strange limbo, probably true but completely unproven. One of the most famous open problems in all of mathematics. Simple enough for a child, unsolved by every genius who's ever tried. You can even find Collatz calculators and visualizers online, built by hobbyists and professional mathematicians alike. In 2019, one of the greatest living mathematicians, Terence Tao, made real progress. He couldn't prove the conjecture completely, nobody has, but he proved something huge, that almost all numbers in a precise mathematical sense do eventually reach a very small value. It was hailed as one of the biggest steps forward on this problem in decades. And even Tao himself said a full proof likely requires entirely new mathematics that doesn't exist yet. It gets stranger. Mathematician John Conway studied generalized versions of this exact same kind of problem, and he proved that some of those generalized versions are formally undecidable, meaning there could be a version of this question that no computer and no proof could ever settle, not even in principle. The mathematician Paul Erdos once said mathematics simply isn't ready for problems like this one. Some universities have even offered cash rewards for a real, complete proof. Entire academic careers have been spent chasing it and have come up empty, because a real proof would need to rule out every possible number forever, without a single exception. And so far, nobody has found a way to do that. Not yet, anyway. It shows up on lists of the most famous unsolved problems in all of mathematics, right alongside some of the biggest names in the field. Maybe the next great breakthrough in mathematics won't start in some university lab. Maybe it starts with someone who just watched this video. Someone who decides to try just one more number. Go on, pick one. Whatever number you choose, watch closely where it goes. Every video on this channel is built around one idea, one pivotal moment that quietly changed everything, explained clearly in under 15 minutes. If that's useful to you, subscribing means you don't miss the next one, and there's always a next one. And if this video changed how you think about something, even a little, hitting like is what tells YouTube to show it to someone else who needs it too. If this one was worth your time, there's another turning point video waiting for you right there.